All right. So we're going to continue our discussion of convective heat transfer today by moving from the analytical methods that we talked about last time to scaling approaches, which is going to be sort of the bulk of the approach that we use for actually doing these problems from here on out. Previously, what we did was we set up a very simple problem, right? For example, last lecture we talked about the gravity-driven flow between two parallel plates. So it was, a couple of parallel surfaces that looked like this with flow, with a fluid flowing between them, driven only by gravity. And what we ended up with was something that looked like a velocity distribution as a function of x. It looked something like this, right? This parabolic behavior, and a temperature distribution that looked like something kind of like this, where we had a T1 and a T2. So the details of these are unimportant right now, but remember the idea behind this, motivating factors, was said what we would want to know as engineers is essentially how much thermal energy per unit time, right, what is Q, be flowing from this plate across the gap into that plate, okay, by action of convection in the fluid between the two plates. So, and we could calculate that, or essentially, if we wanted to calculate that using a convective heat transfer equation, or Newton's law of cooling, we would say that Q is equal to H times the area of the plate times T1 minus T2, right? Where H, and this is the biggie here, is sort of the golden ticket to finding this heat transfer rate. So saying that H is equal to K F dt dx at x equals 0 over Ts minus T infinity. Okay, so by plugging in the parameters that were given, Kf, Ts, and in this case, rather than T infinity, we would say T1 and T2, right? So rather than, this is given, this is given, this is given, and this is calculated. Essentially, what we did was we said, right, we solved the Navier-Stokes equations to get V as a function of x, and we plugged that into the energy equation, which is just a statement of the first law of thermo. And from that, we got T as a function of x. Okay. So with that T of x, we can calculate the gradient to fill in the last piece of information to get H. So it just becomes a matter of, once we have that solution, we just plug stuff in to the calculator and find H. So from H, then, we can find Q. But this is, like I said before, and like I've been stressing up to this point, that's a really laborious process, because many problems we can't solve the Navier-Stokes equations. Even if we can solve the Navier-Stokes equations, some of those problems we can't then solve the energy equation. So the number of problems that can find their way through this and actually give us an exact solution for the temperature, super small. Not really. It's not really a viable approach for the everyday engineer. Okay, to go through this pages-long process of solving these equations exactly. So, what do we do when we want Q, right? Or when we want H in order to find Q in more of a day-to-day setting? The answer to that is using scaling-based approaches. eraser button, there we go. So we saw some examples of scaling in fluids, right? When we did things like the Buckingham pi theorem and dimensionless relationships and correlation. Okay, this is going to be much of the same, but we're going to sort of skim over the dimensional analysis portion and just get into like the meat of these correlations and how we use them. So, right. So as I said before, the key here is H. We want H so that we can plug it into Newton's law of cooling to find Q. But what variables, right, affect H? You know, what are the so H is the goal. What variables affect H, right? This is the list of all possible parameters of the problem that might go into determining H if we were to solve it through this exact method. Okay. Well, we've got, right, the fluid conductivity. That finds its way in right here. We've got the fluid density, right, which is going to find its way in through the Navier-Stokes equations and the energy equation. Okay, it appears in both of those. We've got the specific heat capacity, C, which comes into the energy equation. Viscosity, once again, in both the energy equation and the Navier-Stokes equation. L, and I should mention L here, right, is a characteristic length or sort of the size of the thing we're considering. So if we're talking about flow between two parallel plates, L would, for example, be the distance between those plates. Okay. If we're talking about flow around a sphere, L would be the diameter of that sphere. So L is just sort of a placeholder for whatever length scale is important to the problem at hand. So this one, don't take too literally to be L exactly. We might replace that with a diameter, a distance, as on an ad hoc basis, you know, on a case-to-case basis. L, we've got Ts and T infinity, right? The temperatures of the surface and the flow past that surface. We've got U infinity, right? The velocity of the flow past that surface. And that probably forms a pretty complete basis of the parameters that affect H, right? So we've got 1, 2, 3, 4, 5, 6, 7, 8 sort of independent variables and one dependent one, H. I should also mention, right, that these apply applicable for a given geometry. Now, when I say that, basically, I'm saying if we already know the geometry, what other things could we change? We could also sort of list as another parameter here the geometry of the problem, but we're going to assume that we're considering cases where the geometry is already known, and we're just looking at the ways we could vary, you know, the fluid or solid parameters in a way to affect the heat transfer. So, okay, so, right, this and the example that we finished last time, right, should kind of demonstrate to us that there are a lot of these independent variables that can affect the final answer to figuring out H. So then how we might reduce the number of parameters and simplify the problem comes from a non-dimensionalization process. So the key to reducing the number of independent parameters or variables, right, And the motivation here is to simplify the problem. The key is non-dimensionalization. Now, non-dimensionalization in fluids we completed through the use of this thing called the Buckingham pi theorem, right? Where you said you're repeating variables, non-repeating variables, and you formed a series of dimensionless pi terms. What we're going to do instead here is we're going to do it by a process called inspection. So step one is going to be select a set of characteristic characteristic variables. And what I mean by characteristic variables are these are sort of the broad strokes variables that we think are going to be important to the problem. So things like the free stream velocity, okay, things like the surface and free stream temperatures. If we're talking about, right, the species equation, which we haven't really spent a whole lot of time with, but we'll make sure to do at least one example before we're done with convection, right? Then we'd be talking about the concentration at the surface and the concentration in the free stream. Surface concentration of species A and free stream concentration of species A. So if we take these as our, and then also L, right, which is, we already established, is our characteristic length. So if we take our our original set of variables that we defined up here, we can write out a non-dimensional set of variables in terms of those and these characteristic scales. So what those are going to look like then, going to be write out the independent variables, well, we'll say as dimensionless quantities. So this will be the non-dimensional coordinates. X star is equal to X over L, and Y star is equal to Y over L. Okay, so right, any of our solutions, whether it's Navier-Stokes or the energy equation, right, they all include some variation in X and Y, since we're doing two-dimensional. So this is just a way of taking our X and our Y, dividing by whatever our characteristic length is, and what we should get then is basically a rescaling of our X and Y to something between like 0 and 1, right? We'll have a non-dimensional, say non-dimensional velocities. So U star is going to be equal to U over U infinity, and V star is going to be equal to V over U infinity. So once again, the local velocities U and V relative to the free stream velocity. Similarly, say we have a non-dimensional pressure, which is going to be P star equal to P over 1/2 rho U infinity squared. And for the species equation, non-dimensional concentration, just say Ca star is equal to Ca minus Ca free stream over Ca at the surface minus Ca in the free stream. And then finally, non-dimensional temperature, which we'll call theta star, which is equal to T minus T infinity. So that's what we would ordinarily call theta, right? In some of the problems we've done so far, just the temperature difference between the free stream and some local point would be theta, but that star indicates that we're scaling it by the temperature difference between the surface and the free stream. So you can see here how we have used we've used that set of parameters, right? That set of characteristic parameters that we sort of picked out in order to make each of these key terms dimensionless. And by dimensionless, right, I mean it doesn't have any units associated with it or any dimensions. There's no length. There's no actual temperature, rather than this being, right, some quantity in terms of Kelvin or degrees. It's simply a scalar number with no units attached. And the other nice thing about this is, as I mentioned up here, generally, right, U infinity is going to be the largest number. The biggest difference in concentration or in temperature is usually going to be between the surface and the free stream. L is typically going to be, right, the largest sort of length scale of the problem of interest, and so each of our dimensionless quantities should, rather than being from some arbitrary minimum to arbitrary maximum, they should be approximately between 0 and 1. Not necessarily exactly. That it's not the case that this is necessarily going to be exactly between 0 and 1, but it's sort of rescaling that quantity so that it's going to be on that order, which makes things nicer in terms of actual calculation, right? Because you can say that if it's near 0, then it tells you, well, that the temperature is approximately at the free stream temperature, and if it's near 1, then that means that, oh, it's approximately the surface temperature. Okay. So now comes the step that is probably the step that's going to use the most ink, which is taking these non-dimensional terms and plugging them into our governing equations. So the way we would do this is, if we sort of as a prototype, if we were to, for example, take this right here, right? We could go ahead and write our dimensional temperature in terms of this, right? We could say that T is equal to, right, this theta star times Ts minus T infinity plus T infinity, right? And then we could write, right, that the derivative of dt dx, for example, would be d theta star dx times Ts minus T infinity. Or, if we wanted to then bring in this non-dimensional x, we could say then that T dx is equal to d theta x dx star times Ts minus T infinity
times, or over L. Okay.
So what we've done is we've come up with a substitution rule where we can take these dimensional derivatives and replace them with derivatives that use these dimensionless quantities times something, some sort of scaling factor. So if we do that to each of our original governing equations, right? Our Navier-Stokes equations, our conservation of mass, our energy equation, and our species equation, what we will hopefully get is a series of equations that have only these dimensionless derivatives and then some sort of scaling factors that we can make some sense of. So non-dimensional governing equations. So mass conservation first. We would write as du star dx star plus dv star over dy star is equal to 0. So this doesn't really look any different than our original version. It's just that now u, x, v, and y are dimensionless quantities, so they've been scaled. Our x momentum equation, or the Navier-Stokes equation in the x direction, would be written u star dt star plus u star plus v star negative dx star plus 1 over the Reynolds number times squared Okay. So the x momentum equation, again, we've got our local derivative term, our convective derivative terms, our pressure gradient, and our viscous dissipation. But the difference here is that, right, once again, none of our terms here have any actual dimensions, right? No units. And we have, instead of having viscosity over here and the density over here, we've sort of grouped all of those scaling factors that come out from the substitution. They've all gotten grouped into one other non-dimensional term of a Reynolds number. Okay. Similarly, if we do that for the y momentum equation, we'll end up with dv star plus star equal to d e y star 1 over Reynolds number squared v star plus d squared v star for d. That should be an x and dy star squared.
Okay. The non-dimensional version of the energy equation. And this is the longest of them. Got d theta star dt, so non-dimensional rate of change of temperature, plus star dt, or d theta star dx, plus one over the Reynolds number times this other non-dimensional term called the Prandtl number, and we'll go over these dimensionless terms in a second. D squared theta star d dy star squared plus this the ratio of what's known as the Eckert number to the Reynolds number, 2 du star d squared plus 2 star dy star squared plus d star dx plus d u. Okay, I'll give you guys a minute to finish writing all those down. I just realized that there's one term in here that we didn't define, which is this T star, right? Non-dimensional time. Typically, if I scroll back up here, we would say that non-dimensional time would be T star is equal to time divided by, it's going to be L for U infinity. So basically, the time divided by the time it takes for flow to move through some that our characteristic length L. Okay. And one more governing equation, which is our species equation for the sake of completeness. dCA plus U star dCA star X star one over Prandtl number, Schmidt number, d squared. Okay, and so there's our governing equation for the non-dimensional concentration of some species A. So if we sort of zoom out here, take a look at all of these together, right? As I mentioned, we see we see these non-dimensional parameters of interest, right? Velocities, temperatures, concentrations that we set up, but we also see these collections of terms, the Reynolds number, and Prandtl number, the Reynolds number times what's known as the Schmidt number. So it makes sense to kind of do a brief overview of what these terms are, okay, and how we would define these. Dimensionless groups. So we are going to have the Reynolds number, which we have seen lots of fluids, right? This is defined as the density times free stream velocity times length over the dynamic viscosity. Or if we go ahead and recognize that dynamic viscosity divided by density gives us something called the kinematic viscosity, we write this as U infinity times L over nu. Okay. So this is the Reynolds number, and is essentially its meaning, its interpretation is the ratio of inertial forces to viscous forces. So a really high Reynolds number basically means that inertial forces, right, those coming from changes in velocity, are much, much more important than forces due to viscosity. So for infinite Reynolds number, for example, that means that velocity becomes unimportant. And if we look up at our x and y momentum equations for an infinite Reynolds number, that basically means that these terms go to zero, which are our viscous dissipation terms. Okay, thinking about that, that simplifies our problem significantly and basically means that our flow, right, would be governed by the temporal rate of change and the convective rates of change, but no longer by this viscous dissipation. Your next dimension in this group is the Prandtl number, which is defined as C times the dynamic viscosity over K, or the kinematic viscosity over the thermal diffusivity. Okay, I should mention that this K here is for the solid surface that is being bounded by the flow. So if we have the flow past a sphere, K here is going to be the thermal conductivity of that sphere. So this is known as the Prandtl number, and this is a ratio of molecular diffusivity, right, which is just a fancy way of saying viscosity, or the diffusivity of momentum, right, relative to thermal diffusivity. PE, which is equal to the Reynolds number times the Prandtl number. Okay, so that shows up right here in our energy equation, the product of the Reynolds number and Prandtl number. So we give that that product a special name. This is going to be equal to, right, U infinity times our length scale over the thermal diffusivity. This is known as the Eckert number. And this is essentially the ratio of the importance of advection relative to conduction. Okay, so right, if convection is made up of our two kind of basic mechanisms of advection and conduction, this is going to tell us how important those mechanisms are relative to one another. So we would expect that the Eckert number, right, if we're considering a case of convection, is going to vary between 0 and infinity. So, right, flow past a flat plate, for example. We've established, right, that right next to our solid surface, right, where the non-slip condition tells us that the velocity has to be equal to 0, that means that conduction is dominant. Right, so if conduction is way more important than advection, we would expect that the Eckert number is going to approach 0. As you move away from that surface and through the thermal and velocity boundary layers to where we're in the free stream and conduction becomes negligible and advection takes over, we would expect that the Eckert number will approach infinity. Okay. EC, which is defined as U infinity squared over C times Ts minus T infinity. This is known as the Eckert number, and this is the ratio of kinetic energy in the free stream relative to the change in enthalpy across the thermal boundary layer. Right, so our kinetic energy is going to be dependent on the square of the velocity, and you can see that, right, if C is our specific heat or specific heat capacity, then C times this change in temperatures is going to give us some change in thermal energy. So it becomes kinetic energy over a jump in thermal energy. And this shows up, right, the Eckert number there shows up in our energy equation right here. Okay. And the last one, and this only shows up in the species equation, is what's known as the Schmidt number, SC, which is equal to the kinematic viscosity over dA. Right, and dA, if you recall, for the species equation, this is similar to alpha. Right, alpha is our thermal diffusivity. dA is our concentration diffusivity. So this is known as the Schmidt number, and is the momentum diffusivity over mass diffusivity. So the relative rate of momentum spreading out due to the action of viscosity or friction relative to the spreading out of some concentration. So Okay, so, right, this has been a lot of definitions. Fortunately, there's not a whole lot of way around that. We have to slog through these definitions before we can start using them. But I don't want to lose sight of kind of the purpose of going through this whole process, right? Which was ostensibly to simplify the process of finding the goal, which is simplify the goal of determining H for convection flows. So if we return back to H, okay, where did it go? Remember that H is defined as the fluid conductivity times dt dy, evaluated at y equals 0, divided by Ts minus T infinity, right? So if we went through the same process, okay, we said that if we substituted in the dimensionless temperature and dimensionless y into here, what we would end up with is basically H is equal to Kf times d theta star dy star evaluated at y star equals 0 over Ts minus T infinity, but times actually Ts minus T infinity over L. So if we went ahead and we, right, canceled terms here, Ts T infinity, or minus T infinity, we can cancel those over. If we take this L and we move it over here, take this K, move it over here, what we end up with is an expression that looks like H L over K of the fluid is equal to y star over y star equal to 0. Okay, so these terms are both dimensionless, as we found before. So over this side of the equation has no dimensions, which means this side also has to be dimensionless. And this is an extremely important dimensionless group that we will call the Nusselt number. So Nu is equal to HL for Kf. And this is known as the Nusselt number. So I've given this its own section, right? I didn't list it up there with the others because the Nusselt number, right, contains H, which is sort of that nugget that we're looking for. And the beauty of the Nusselt number is that the Nusselt number is itself generally, well, actually I should specify that this is known as the local Nusselt number because it's defined with respect to our local convection coefficient H. We also have something called the Nusselt number, the mean Nusselt number, which is the average convection coefficient times L over Kf, and this is the average Nusselt number. And the beauty of these is that the Nusselt number, the local Nusselt number, is a function of, right, our position in space, which is the dimensionless x, times the Reynolds number and the Prandtl number. Okay. And the mean Nusselt number, then, because it's been averaged over our surface, stops being a function of x and simply becomes a function of the Reynolds number and the Prandtl number. So what I want to end on is, I know today's been sort of abstract, lots of definitions, but the important thing is that we have taken, right, this case where we said h is some function of, right, this whole mess of variables, rho, L, C, mu, Ts, T infinity, U infinity, and we have boiled that down into something that says the Nusselt number, which is equal to, we could go ahead and say this is h bar actually. H bar times L times Kf is a function of just two dimensionless variables. So if we were trying to, for example, make some sort of design database, all right, if we were engineers in the lab, which some of us are, trying to come up with a kind of a table of h values that we could use for variations on a design. If we were to go at it directly, okay, our design of experiments would have to include 1, 2, 3, 4, 5, 6, 7, 8 independent parameters. If we wanted to do a full factorial design, for example, with 5 treatment levels of each, then we would end up with, right, this exponential quantity that involves probably tens of thousands of individual experiments. On the other hand, if we were to recognize that all of that important functional relationship has been boiled down to this by non-dimensionalizing our governing equations, our experimental design now only has to include 2 independent parameters, which means if we want to do 5 treatment levels, we end up with just 5 raised to the 2, or 25 experiments, as opposed to 5 raised to the 8th. All right. So actually 5 raised to the 8th is going to be millions of experiments. Let's figure that exactly out. 5 raised to the 8th power is going to be 390,625 experiments. It's a long time in the lab. Okay, so I had an example set up, but you know what we're going to do is we're going to go ahead and leave the example for next time, and I'm going to close on just a couple of kind of important sort of notes, some things to remember here, which is that in all of this, these are kind of common pitfalls. So L, I want to write things to remember. L is our characteristic length, which means it can be any important linear dimension of the problem that we're considering. I said this earlier, but it bears mentioning again. And I want you to remain cognizant of the difference between Kf and just K. So Kf, remember, is our fluid thermal conductivity, and K is our solid thermal conductivity. So if we have a fluid flowing past some solid object, right, Kf and K are not the same thing. They're both thermal conductivities, but one is for the fluid and one's for the solid. And for that reason, right, the Nusselt number, it looks similar to this thing we talked about before called the BO number, where the BO number simply was HL over K. The Nusselt number, right, is essentially the same thing. The relative rate of convection relative to conduction, but in the fluid as opposed to in a solid. So we'll close on that. We'll wrap this back up and do the example first thing on Friday. So have a good day, guys.